Hello everyone, my name is Aku, I'm a father of a flipper, and today we will talk a little bit about embedded systems in general and their software in particular, and we will take a small discourse in what kind of uh, MCUs we're using, CPUs we're using, how all these things works in terms of connecting it with software, what requirements, and how to make the code that runs on those systems safer. Yeah, so today's agenda. What is embedded systems in general? Hardware, software, different tricks from Flipper devices team. And question and answers if there will be any. So what is embed? So we'll talk about embedded systems, classification, and a little bit of history. Today's talk will be a little bit short. I will try to squish too many things. So if you need more details, you can find them online in Wikipedia, or some additional details I will publish later on our website and with this presentation. Okay, so when we're talking about embedded systems, what it is, it's usually part of something bigger. It's usually something that performs one specific task. And because of that, it doesn't have to be as flexible as general computers. For example, your CPU, your desktop PC, it got all additional buses to extend it. It got replaceable memory, things like that, and usually it got more resources that you actually need. And that's what makes embedded system different. They usually get enough resources to perform their task, and that's it. And often those systems are designed to perform real-time tasks. And by real-time, we mean that something that reacts on event in a specific time. So, and I'll tell a little bit more about why it's important and what kind of system actually uses that. So, we can classify all those systems into, by, first of all, those systems starts with a task, like what exactly are they doing. For example, you have a car, and inside of your car you have ECO, which performs fuel injection, engine control, and the main task is fuel injection, engine control. And everything else is built around this idea. So usually that's where we take in specific MCUs, specific peripheral, and that's how we build the whole system. So that's this technical description for the whole system. And when we know what kind of main task do we have, we can decide like, okay, so what computational power we need. So is it enough to have like a small MCU, let's say something like maybe 8080, maybe 8051, maybe something a little bit faster. Maybe we need already more than ARM CPUs from M series, or we need so much processing power that only A cores from ARM will be sufficient for us. And then we decide like, okay, so we have also the system, and the system probably is a hard real time, or it can be soft real time, or it's not real time at all. So what it means? So imagine we have like some sensor in the engine, and we have event from this sensor. Let's say our flying wheel at some position. And that's where we need to react. We need to react immediately, and we need to know if we need to inject fuel right now or not. And that makes the whole system hard real-time system. And hard real-time systems, they don't have space for error, nor in time, nor in any computation. So, and it means that this system should get enough processing power to do the tasks. And usually it uses specially designed MCUs that can, with special cores, that can actually handle real time. Because we know that, let's say, a long time ago when computers just started, interrupts was almost immediate. It basically, you got the signal, you got the interrupt coming, and then it immediately delivered it to interrupt handler. Now we got much more complex CPUs with architectures that require some time. Let's say if we're talking about modern ARM cores in M series, you usually need at least 20 clocks before this interrupt will be delivered. And in some cases, if we're talking about big A cores, interrupts can take even longer to be delivered. Plus, there is some special kind of architecture designed specifically for real-time tasks. It's called ARM-R. And that's what you would probably want to have if you're designing some hard real-time things. Soft real-times usually means that if you're missing deadline, then system is not going to crash. Let's say it's not plain, it's not going to dive and crash. But you still would like to at least keep some kind of real-time, to react on some events in some predictable fashion. And then we have like non-real-time systems, a system that doesn't require like immediate reaction on the event. And those systems can be built with general purpose CPUs, like big ARM cores. A good example is Raspberry Pi. So yes, it got GPIO, yes, it can be connected to something, but the reaction time usually doesn't satisfy nor soft real-time nor hard real-time. Then when we know, like, okay, what kind of CPU or MCU we're using, we need to decide like, what kind of interfaces do we have and interconnect. So the simplest one that probably every one of you know is UART. It's a universal asynchronous or synchronous asynchronous interface. It's a serial interface, and usually it's a little bit slow. So you can get, let's say, 4 megabaud, but it's probably not that fast. Then we have faster buses, like we have parallel buses, serial buses, SPI, I2C, LVDS, and a lot of different things. And all those small things you have to keep in account when you start to design software for all those things, because some of them is actually require your software to react on those receive or transmit events in predictable fashion, and that's where real-time becomes important. And then we got the whole new area of power consumption. So there are devices like the one that connected to power supply or your power plug. There's no problem with if they consume a little bit more than a traditional device or your mobile phone. But it actually do matter when you have some kind of mobile device that you would like to have at least for one day in your pocket. And that becomes a little bit difficult because like not all architectures was designed to be power efficient. Some architectures simply missing any power saving features. And if you get specific requirements like, okay, I have an embedded system that should last longer, should, let's say, live 1 year with a battery, then you probably would like to choose appropriate architectures and hardware for it. Yeah, and obviously, software stack, because some architectures, some MCU architectures, actually not that flexible. Let's say we got 8-bit architectures like AVR. Yes, you can write quite complex, sophisticated programs with it, but there are some limitations, and it will be a little bit more difficult to run a real-time operation system on it than, for example, on modern ARM cores. And if you're planning to do something complex, let's say you know that inside of your system you will have multiple tasks, and those tasks will collect, let's say, data from multiple different sensors asynchronously, you definitely would like to have, would want to have something modern, something that's designed for real-time operation systems. Okay, and let's dive into history. So embedded systems, they started with the discrete components, like some kind of computing module, purely built with the logic elements or even discrete components like transistors. And that was like a hardwired systems. So once it's designed, it always behaves in specific ways. And then in the 70s, we got our first integrated CPU from Intel for 4004. And Obviously, you cannot run just 4004. You still have to have a couple more components like memory and ROM, but still it was a big step forward. And that's where we started to design to offload some part of the, let's say, complex logic into those systems. And then in 70s, 80s, we got more architectures coming. We got first PICs, we got first Motorola architecture, M68K. And then in 80s, we got first 8051. It's the first programmable microcontroller that you actually can use in kind of standalone mode. So it's already got memory, ROM, and you can just write a program for it, program it, and let it run inside of your system. And then a couple more interesting things happened back then. So there was an area where no one yet came to. Just imagine that you have some part of the system that you kind of can program it, but it just doesn't make sense because this part of the system always performs exactly the same logic, and it doesn't have to be in software, and software is actually slower than having this thing done in hardware. And let's say you don't want to use like multiple ICs with logic elements, and that's where first FPGA and CPOD came. So what it is? So FPGA, it's a field programmable gate array, and CPOD is programmable logic. So general idea is very simple. Let's say we have a chip with different elements, like logical elements, maybe additional blocks. And we can just connect them in the order that we want. So, and that's what made this thing special. So instead of writing the software, you can write the hardware. And that's what really simplified design of the complex hardware systems where you need hard real time, and let's say you have a motor, and you need to control it, not just motor. Let's say you have a synchronous motor that requires quite complex logic to control gate drivers, and that's where FPGA is actually quite good. But not only that, rather all kind of different things that cannot be solved in software, but can be solved with FPGA. Okay, and in the 90s, we got first architectures that actually became like super popular. So AVR, and we also got first CPUs, MCUs for embed with a big cores like ARM A series. So obviously ARM A series, it appeared quite recently, and before ARM 8 series, we were having 962, and before 962, we were having even previous cores. But they were already quite powerful enough, and they changed how we look at the embedded systems. If at the beginning we were seeing them only as some kind of supplementary system that kind of executes only one task, so with new cores, with new high-performance embedded systems, we already started to have proper user interface, all kind of additional features, Ethernet, IP stack, and all it arrived starting 90s. Then in year 2000 and later, we got the new generation of popularizators who actually brought us all those simple and wonderful things like wiring, Arduino. It's really simple. So hardware always was kind of complex because you have to think like how to connect things with each other, how to properly design analog part, a digital part, and then you will have to write the software for it. And in some cases, like early architectures, they kind of, some of them even didn't have compilers. So you were programming them with a pure, just inputting instruction opcodes. And in 2000, with arriving of Arduino, it became much more easier and opened the door into embed to many people who previously were thinking that it's too complex. And then Arduino also was quite cheap because hardware in general, designing hardware, uh, producing hardware, especially in small quantities, it's a very expensive thing. And dev boards in general, they are quite expensive. And for some things like FPGA from Altera or Xilinx, dev board kit may cost up to $100,000. And that's only the base part. You still have to design, let's say, some additional blocks that you want to control with this FPGA. And arrival of cheap dev kits like Arduino kind of lowered the entry to almost everyone. And then in 2010, we got a bunch of, so Arduino was like the lowest in terms of computing power. So what about like the big boards with the big CPUs? And in 2010, we started to see cheap dev boards with powerful MCUs too. And with Linux, and like one of the most well-known is the Raspberry Pi. So now you not only can write in C or C++, you can use almost any language, and you can use Linux, and you can script everything. And that's also simplified life for many developers who didn't want to invest a lot of into embed, but wanted to have a control of physical world from his computer. And now we see something a little bit different. So we know that, okay, we got area with hard real-time, we got area with non-real-time systems, and usually you have to, let's say you're designing some kind of device where you want to have both of them. Let's say you want to have Linux with user interface, and then you want to have hard real-time to control something that's kinda don't like when you're missing deadlines. And now we have all of them in one package. Even more, we not only have like big ARM cores or small ARM cores in one package, we also have FPGA in the same package. And that's new multi-core hybrid systems on chip. And all kind of variants right now available, and in next year, our partners, Nordic and ST Microelectronics, are also releasing a bunch of new chips with hybrid architectures. They even combining RISC cores with ARM cores and with multiple, like one die with 6 cores. And some of them low power, some of them high for processing, and some of them for designing new peripheral buses. Let's say we want to design something that not yet exists in silicon. You will be able to do that with those blocks. So a little bit more about hardware. So we will start with CPU, MCU, and ASICs. We'll talk about what it is, what are we using it for, then FPGAs, CPODs. A little bit about peripherals and interconnects. So the most popular things in embed, and at least we're not going to talk about things that was like 20, 30 years ago. We will talk about what we have right now. So, and there is like 3 main groups for CPU, MCU, ASICs. So CPU is our central processing units, quite powerful enough. And when we're talking about them, we're usually talking about ARM A cores, sometimes mixed with R cores. Then we do have some M cores that's actually powerful enough, but they usually lack of memory management unit. And because of that, we cannot run Linux on them properly. And then we have x86, and some systems were specifically designed, like the one by AMD. It's with Geode series. It's probably a little bit obsolete right now, but still that's what we use sometimes. And then x86 also use it in some high-performance network routers as additional cores for traffic processing, or as a supplementary core for controlling the fabric itself. Then we have a special class of the CPUs, which we call MCU. They're usually a little bit simpler. They don't have memory management unit. They're specifically designed for embed, and they usually got additional peripheral blocks that can control different buses. Let's say additional SPI, I2C, LVDS, timers, all kind of timers, comparators, analog to digital converters, digital analog converters, all those things usually just integrated into one chip. In addition, so CPU usually don't have memory on board. Obviously, they have a little bit memory just to start the whole thing. To enable memory management unit, map external memory into your address space, and then just load your big application or your kernel and start it. If we're talking about MCUs, they usually don't have external memory. In some cases, you can connect it, but you can perfectly work with it even without additional memory. And it means that it got RAM and flash memory right on the chip. And probably the first one that actually started to combine all those things together was the PIC and AVR microcontrollers. And some of them are actually quite specialized. So we can find, for example, so 8051. This is one of the oldest architecture. The originally was designed kind of for microcontrollers. And what is important that most of the commands that this architecture supports in modern MCUs, they just executed immediately in one tick, in one clock, and that makes it quite nice to do some, let's say one of the probably most interesting things is USB, especially USB 3 and upper, and there is a vendor that designs kind of bridges that between USB and some parallel buses. It's called Cypress, and they usually got 8051 core that responsible for like a negotiation and things like that, and everything else is just offloaded into specialized hardware blocks. Also, if you heard something about Expressive and ESP32, they use this Extens architecture, Stencil. And actually, that's only the most common one. There are a lot of different architectures, a lot of chip vendors who are using specialized architectures. Some of them, for example, design it for specific tasks like digital signal processing. Some of them are just designed to be as simple as possible, as close to hardware as possible. All kinds of things exist, and in some cases it's very difficult to find exact architecture that will suit to your needs. And ASICs, so basically it's specialized ICs, like the one we can use, that usually use it in network switches, in routers. They usually have like general purpose core that's responsible for controlling. So general purpose core is a control plane, and then you have specialized silicon that, for example, performs switching, performs packet handling, and this is like a data plane. And control plane and data plane, control plane usually just configures data plane to perform some specific tasks, like where we can roll those packets. And in some cases, when, for example, we want, let's say switches usually performs tasks on L2, but in some cases we would like to perform some L3 tasks on the switch itself. And without building specialized blocks to handle L3 tasks, we can just grab packet from L2, process it, and then put it back into Fabric. And that's what usually ASICs do. Not only that, but like a huge amount of different things, like radio, some really specialized ASICs exist for it. And all of them is actually embedded. And then we have a special category of things, FPGAs, PLDs. So it's all about programmable logic, all about building something that will be hard real time and something that usually fixes it. So it's not, obviously, like a new FPGAs, new PLDs actually can modify themselves on fly, which brings actually quite interesting possibilities. But in general, those things are programmed once on the system start, let's say, and then they just perform one specific set of tasks, but in hard real time. Usually, FPGA or SPLD, it's just a bunch of logical elements and interconnect fabric. So basically, the firmware for your FPGA SPLD is just connecting those blocks together and building the chains of logical elements. In some cases, we can add to those elements specialized blocks, like the one for PCI or USB. In some cases, we can add radio, high-speed ADC, or DAC. And now we also have a bunch of things like hybrid SoCs with FPGA and general purpose CPU, like ARM A cores or ARM R cores. The most probably well-known is Xilinx with the UltraScale series and Zynq series. And all kind of different additional chips that we can have in our embedded systems. Some responsible for Wi-Fi, usually we got some kind of interface standardized by appropriate station, like Wi-Fi and Bluetooth got standard for host control interface. Usually we work with it through the SPI, and it's plus minus simple to integrate into almost any embedded system. And then we can have all kind of different buses, CAN buses or NET bus, usually with additional controllers or not. Sometimes all those things can be embedded into MCU itself, and sometimes it will be some addition. Yeah, so if we're talking about MCUs and CPUs, use it in embed, you usually got a bunch of different buses to connect all those different parts of your system together. If we're talking about, let's say, cars, the most popular one will be CAN bus, and usually your car got at least a couple different CAN buses with a different speed and different level of redundancy. Let's say we have engine, then brakes. This probably will be something the most important. It will be one isolated CAN bus, and then we have, let's say, lights and the body. It usually second one less isolated, and we do care about errors in the first one, and the second one is actually, if something goes wrong, it's okay. And all kind of parallel buses like 8080, 6880, 6800 for connecting some displays or legacy things, and LVDS. All those buses also can be either just a single wire with high level, low level, or it can be differential with the appropriate front end to handle all those noises and subtract them. Software. So in general, the stack is plus minus same as we use on the traditional PCs with some additions. First of all, usually we have specialized IDE for developments. They usually integrate additional packages that are able to do chip introspection, peripheral introspection. Some of them got better integration with the debugger itself. Some of them got extra integration with debugging tools and in-system programmers that use it for programming your chips. In some cases, you may want also to do like a power profiling, and a lot of modern tools from ST Microelectronics and Nordic also integrates this feature inside. So it's like at the same time you can debug your chip, see what exactly happens, like trace interrupts, trace let's say function calls, and at the same time see the power consumption of the whole system or specific blocks. And after IDE, we have usually compiler. So some compilers like Clang or GCC, they also got different ports to like big MCUs and small MCUs. Some of them was forked and got like a special version, like the one for AVR architecture. And also we got a lot of proprietary compilers for specialized architecture, especially the one for DSP. Those like the special kind of it on its own, and compilers for them is something that you probably will not see someone designing in as an open source. And compilers, especially closed source area, is compilers for FPGA. And then when we have a compiler, so we need some standard libraries. And the standard libraries that we're using for our traditional application on, let's say, Linux, macOS, or Windows, they're a little bit too thick to be just use it on the such a small devices. And another problem with them is that they usually expect that reentrancy kind of will be synchronized with your kernel, and reentrancy handled in a way when it's very expensive. And that's why we usually would like to either use specialized libraries for embed, or in some cases we would like to use, we would like to just completely abandon them and use our own libraries. And we also got a bunch of different operation systems for embed, starting with a big one like Linux, and then we get the whole area of real-time operation systems, and then we get in-system programmers that we will need for debugging and debuggers itself. So a couple most well-known IDEs that currently used. So VS Code suddenly became quite popular, and there are a lot of plugins and things like Platformio that allows you to easily port libraries between different architectures for embed, and also easily set up the environment for development itself. And then we have specialized IDE from vendors, your chip vendors. For example, ST Microelectronics got their own IDE. It's called STM32Cube IDE. Then Sega IDE use it. Obviously, it can be used with almost any chip, but in addition, Nordic also got the free version for those who are writing software for Nordic chips. And then we got one of the oldest, it's ER. It's not only IDE, but they also develop a compiler for multiple architectures. And then we got Arduino, which actually not like a proper IDE, but still many people use it for development, and much more. So compilers. So usually when we're talking about compiling software for embedded systems, we got choice. We got a bunch of open source tools like Clang and GCC, and a small device C compiler. And then we got some proprietary things like compiler from ER. And also some of the vendors do their own forks. For example, there is a fork of Clang by ARM Foundation, and they do develop their own proprietary package with additional fixes and optimizations. For the Flipper, we actually using just the GCC, the standard version from GCC itself. And okay, so now we can compile our code, like what kind of libraries and platform libraries we're going to use. Starting with the libc, we usually see new libc as a base for almost all toolchains that's right now available from different vendors. But there are a lot of problems with it. New libc wasn't designed for embed. Like, it was kind of designed as a replacement for GNU libc, but it doesn't handle all tasks that we need to handle on microcontrollers. For example, many functions, they're not thread safe, they're not reentrable. And reentrancy kind of possible to integrate, but that's the task that you usually do on your own. Also, some functions like printf, they may behave incorrectly, especially in multi-threaded environment. If, for example, you're combining new libc with FreeRTOS, you definitely would want to guard a lot of different things inside. It's not like it's impossible. It's actually possible. That's what we did with Flipper, the toolchain that we designed, the build system, and the glue code that works with libc is kind of trying to make libc usable for microcontrollers. But there are there are other solutions on the market, and especially if you're willing to pay, ER can provide you the library that actually was designed for microcontrollers and behaves properly. Then if we're talking about like systems, embedded systems with Linux, we're actually not limited with GNU libc. We can use traditional GNU libc, we can use Muesli libc, and all other kind of libcs that are currently available on the Linux itself. Then we usually have a special layer which is called CMSIS. If we're talking about ARM cores, we have CMSIS. So CMSIS is basically a collection of different layers, starting with CPU itself. So basically, it's a set of headers that explains like where in your CPU, like what exactly you have in your CPU, what kind of commands you can use, and it kind of wraps it into human readable form. And then on top of the CPU package, usually each vendor that designs some kind of microcontrollers or big CPUs, they add additional set of headers that use the first one as a base, and then explains like where exactly additional peripheral blocks map it in this microcontroller. And they also gives you like vendor how. So vendor how already, so for each block define it in CMSIS how, we can also add additional set of methods, how to control this block, how to start it, how to stop it. Let's say we have UART block. We definitely want to have at least receive and transmit methods. And that's what vendor how usually do. And then on top of that, when this microcontroller place it into, let's say, on some board with specific blocks, specific connectors, specific, let's say, power supply, you probably would want to also explain like what kind of things around this board. And that's what vendor board support package doing. Obviously, that's just a base. The more complex things you develop, the more different things you would like to incorporate. In some cases, that will be third-party open source tools. In some cases, it could be proprietary libraries for digital signal processing, file systems like a LittleFS, and that's where things become a little bit more complex. So originally, all embedded systems with small microcontrollers, they usually were doing one specific task, and there were no need to do like multiple things in a parallel. And the program design and program flow was like a super simple. And then microcontrollers became bigger, and the set of tasks became bigger. So, and instead of having, let's say, 10 microcontrollers doing different jobs, but just one task, we started to think about, okay, now we have those new set of tasks. We would like to have microcontrollers that actually can process more and actually can perform multiple tasks simultaneously. And that's where ARM M cores arrived, and they brought us like a native support for different real-time operation systems. So by native support, what it means that you can have so when you have one application, you usually need only one stack. And when you have like multiple tasks in your application, you would like to have, so each task, you would like for each task to have its own stack. And like all architectures, they were only able to manipulate with one stack. And starting with M cores brought us support for multiple stacks. So you have a main thread, and then you have ability to do context switches and change stacks on the fly. And that's where new set of operation systems arrived. So probably the most popular one is ZephyrOS, then FreeRTOS. Also, some hardware vendors like THAS Instruments got their own operation systems like TI-RTOS. Usually those operation systems started long time ago, and then the company that started this operation system was bought by one vendor, and then it became like a default operation system for, let's say, THAS Instrument, for example. And then we have a Micrium OS, one by C Labs, also use it on the microcontrollers. Some big open source projects like ChibiOS. And obviously, if you have some powerful ARM cores, or Or we actually can run Linux on devices without MMU. So even smaller ARM M series can run Linux. It's not like it kind of makes sense. It actually doesn't make much sense, but you can do it if you want. Okay, and so when we compiled our application, let's say we took our GCC, we took a linker for it, we took standard libraries, and we compiled the application. So now we want to put this application into our device. If we're talking about traditional computers, we just copy it on our hard drive, and that's it. But that's not that simple when we're talking about hardware. So usually each microcontroller got its own special debugging port. It's either JTAG or SWD or some other transport that allows you, so basically it gives you control on the computing core itself. It allows you to define when exactly, let's say you want to stop at some specific instruction at some specific place. You just program through the DAP specific address, and that's where microcontroller automatically stops when reaching this instruction. And that's why you need in-system programmer. And there are a lot of them. Some of them are like a kind of semi-standard, like ST-Link. Then Seger got J-Link, which supports a broad set of hardware. And then a couple open source projects like Blackmagic, OpenDAP, and usually different vendors, they design their own debuggers. And for some specific reasons, for some specific needs. And in some cases, like with Nordic, with Labs, they can have debugger embedded in the dev board. So you can write software without thinking like where should I find this debugger, what kind of debugger will work with this board. Anyway, this debugger you connect to your PC, and then with a special software you can just upload your ELF into microcontroller that you would like to program. And when your software is already running on UMCU, you would like to debug it. Obviously, some architectures are not debuggable. Like they just don't have debug port, like at all. Like all 8051, they just don't. You either did a mistake and it just stopped, or broke your system, or maybe burned itself, or it works. So those systems usually we debug it with printfs, or the simplest way to debug is just to control the pin itself. You just set it to high or to low. And even with modern software, in some cases, printf will be too expensive, and you would like to use just a direct control of GPL. And you have your IDE, you have your GDB that will allow you to debug your file, but you need one more component that will be a bridge between GDB and in-system programmer. So probably most popular one, most open source one is OpenOCD. So it's a GDB server plus additional features, plus additional things that it basically allows your GDB to connect to your ISP and then to connect to your computing core inside of your MCU. Also, there are alternative GDB servers from specific vendors like Seger. Also, for ST-Link, we got the package from ST Microelectronics. And all those things may be very useful when you want to debug your MCU. So, couple tips and tricks from FreePRTIM. So, we'll talk about like a general safety guidelines, like what you should do when you're just writing your software. We'll talk about some additional hardware that you got and probably would want to use for adding additional stability to your software. And then how you can improve the whole thing with continuous integration, continuous delivery, and static analysis. If we're talking about small ARM cores and small systems with a small amount of RAM, so one of the things that usually people do is allocating everything at the compile time. So you just say, for example, there is no dynamic allocation in your software. If there is no dynamic allocation, then it means that your heap cannot be fragmented to the point where you cannot allocate things. And that's what actually becomes important when you have a small amount of RAM. Especially it's important because in big systems with MMU, you actually can rearrange your physical space on fly. Like you can just map blocks and then you can, let's say, transparently for your application on the kernel level, you can change, you can copy data from one block in physical memory to another and then just change mapping. So for the program that's running in user space, there will be no changes. But for the kernel, you will be able to defragment your memory space. That's not the case with microcontrollers because we don't have memory management unit. And even more, even in some cases, so another thing that is important. So memory allocators that use it on desktop, they're usually different in the nature. They don't have to be real-time allocators. They don't have to be predictable in terms of how much time we're spending in them. And that makes them unreliable for real-time operation systems. And that's why real-time operation systems have their own allocators. They're usually trying to be the constant time allocator. So it means that they definitely will do their job in specific amount of time, strictly defined. And that makes them less optimal in terms of memory allocation. And if you do a lot of allocations, in the allocations you may find yourself with a highly fragmented heap, and at the end you will have to crash your device. And that's what brings us to the second topic. Okay, so if we having static allocations or dynamic allocations, it doesn't matter. We still have to do asserts. So we have to think about two things. We need to crash as early as possible. So we need to check all states and all variables that we're feeding from one function to another. And that really helps, like just putting asserts helps a lot. It's like a unit tests where you can do unit tests. And the more asserts you have, the bigger coverage in your software, the better. And that also allows you to crash early. So one of the things that you would want to do in embedded systems, like if something goes wrong, it's better to crash. Because in the desktop systems, let's say we wanted to allocate the more memory than we physically have and the more memory than we actually can allocate with a swap and all those features enabled. And that's the point where your OM killer probably just will kill your process and just release all the resources you were trying to allocate. And that will be totally fine. But on embedded system, let's say we reached the point where memory fragmentation, heap fragmentation became, let's say we can't allocate next block because of the heap fragmentation. So what should we do now? And the only option for you is to crash. And the earlier you will do that, the better for you, because the easier to spot those issues in development and fix them. So also, one of the things that we do with real-time operation systems, we do avoid recursion, not only because that kind of makes everything unpredictable, but it also because of the stack. So we do have, with real-time operation system or without, we have a fixed amount of RAM, and we definitely don't want to go beyond the stack. And usually, let's say, like most of the tasks on the Flipper have, let's say, 1 kilobyte of stack or 2 kilobyte of stack. That's actually not that many. And if you will be not careful and allocate something on stack, like let's say we want one array, let's say 100 bytes, and then you call another function, and it also holds 100 bytes on the stack. And at the end, you will find that your application is crashing. So avoid recursion and track stack users. Also, with a libc, libc contains kind of safe functions and kind of not safe functions. And by not safe, what do you usually mean? So the one that doesn't gives the constraints on how much data, let's say, we process. Let's say the good example is string functions, the one that just accepts the string and then do something with it. So what if your data is damaged? And at that case, if you don't have a limit, you just will continue processing. And with microcontroller, no one will stop you because your address space is kind of not limited. And it makes sense just to remove those unsafe functions at the link time. Just remove them completely. So in case if your developer will try to use them, he will be unable to link his executable. So memory allocator. Also, one of the things that we found like super useful is to change the behavior of the libc. So we have a malloc, we have a free, and when they allocate memory, they don't give you a promise if it will be clean or not. So what we did, we actually started to free memory. Not only, we started to clean up memory on allocation, so basically filled with 0. And then on deallocation, we also cleaned with 0. And that helps to find a lot of different issues with use after free and with something that you forgot to initialize. That's actually quite common issue in C, where someone allocates the block and then thinks that everything fine with it and it got clean zeros in it. And yeah, and obviously different kinds of corruption checks. For example, our allocator kind of checks if the boundaries were so it's a block allocator, and each block got special pattern at the beginning and the end, and if it's damaged, we immediately crash the system. But that's only in software. But 20-30 years of microcontroller development brought us a lot of different tools that we also can use to assist our software to be smoother and to run better. And one of the two, actually we'll talk about two different blocks. It's a memory protection unit. So memory protection unit was designed to just to protect access to the memory from your microcontroller. The good thing about it kind of, you just tell him, okay, I have a memory from this address to that address, and I want to make it read-only or write-only, or I want to just prohibit, or maybe I want to just notify to interrupt another task that someone is trying to access it. And three things that we're doing with memory protection unit. So first of all, with ARM cores, your application starts at 0. So we're starting, our interrupt vector is at 0. And also, we usually do mistakes where we're trying to do something with null pointer. And in order to catch those events, we can just protect memory at 0 with a memory protection unit. And every time when we're trying to dereference null pointer, we'll get memory fault by MPU. Another thing is we got a stack. How we can know that we kind of fucked up our stack? It's actually also quite easy. We can hook, when we're doing context switch, we can make a hook in the operation system. And since we know the size of the stack, we know where it's ending, we can protect, let's say, a couple additional machine words at the end. And next time when we, let's say, go beyond the stack border, MPU also will tell us that something went wrong and we need to check our code. Also, that's probably the most simple MPU usage. For those operating systems and those, let's say, software that specifically designed to be working with MPU, you can also extend these things. You can extend MPU support in your operation system to the point where, for example, your task will be fully isolated and it only can access memory, let's say, allocated to this task, including the stack allocated to this task. And to forbid this task to corrupt memory to do something with memory outside of this sandbox. Combining it with different user modes, you can achieve actually quite good isolation on the level with big operation systems like Linux. And then, since debugging of hardware is actually quite complex, in some cases you may find that, let's say your debugger is very, you just cannot use your debugger, you just cannot design, let's say, script with your debugger to catch some specific things. Like, for example, you do the dynamic memory allocation, and then you do something with this memory, and then someone corrupts this memory, and you don't know who exactly corrupting this memory. And that's where you can use another thing is called DVT in ARM Core OS. It's a debug, watchdog, and trace subsystem. So what we're doing, we're using watchdog capability. So basically, when we see that some corruption happens in some specific region, and we know between which events this corruption happens, so at the first event, we usually just protect this region with watchdog, and then when someone is trying to write it, we will get interrupt, and then we will identify that, okay, someone is trying to write this thing, and we need to debug it. Obviously, there are some caveats, like the one that I mentioned about interrupts on ARM cores. They're not delivered immediately. You'll have to wait at least 20 cycles, so you'll have to go back in your instruction stack to find what exactly happened. But still much better than not having this subsystem. Other MCUs, not only ARM cores, got those debug capabilities, but you will be able to find them in specific instruction set documentation, specific architecture documentation. Okay, and at CI/CD, we also can do some additional things. So obviously, code review is a must. Just sometimes we found a lot of issues where the person just forgot to change variable name or forgot to set it, and on the review we were able to find it. And a couple more things. So since our systems don't have right for a mistake, they don't have a chance for anything go wrong, we would like to enable all warnings, like all warnings that we can enable, they must be enabled. And then we make all those warnings errors. So yes, it is quite painful sometimes to fix them all, because some of them, like casts in C, they may be totally valid, but you still have to put cast in each and every place where you do this type conversion. It's inevitable, but that makes your code much safer. Then we do have like a multiple build options with different compiler flags. And what you would want to do is to build all those options at the CI/CD. Also, in our case, we kind of produce the compact version that disables some debug features. So we're actually testing both of them, the one with debug and without debug. And unit tests, surprisingly, you can do unit tests on modern, not on all platforms. Let's say AVR probably will be possible but painful, but with modern ARM cores, it's actually no problem. And you can have a special firmware that basically got unit test coverage for the whole system, and that's what we're doing. We're covering everything, starting with software synchronization primitives, ending with hardware, and even testing some capabilities. And in addition, obviously, we got continuous integration, where we checking. So the same type of continuous integration that we're using for, let's say, web. We have a browser, we have something that controls browser, and we got the same system that basically takes Flipper, and then it controls it, and then it moves it to different cards and tests every card if it's reading and if it's data that we just got from the card, exactly the same as it should be. And two more things. It's a static code analysis, so probably at least use Clang, because Clang already got some basic but quite solid capabilities to analyze your source code for mistakes. And in our case, we're using open source version of PVS Studio, which also do the analysis a little bit deeper. So it basically checks everything that happens in your C code and then notifies you if you are using it wrong. It's obviously those tools are also not perfect. It's like having all warnings enabled, but at least in the cases where you do mistake, they will tell you about it. And in addition, we do so. One of the things about small embedded systems that you have RAM and you have flash, and you're also writing in C. You're not writing in assembler anymore. And writing in C actually allows you to make a mistake. Like, just imagine you have a constant data that you're not going to change. But this data just must go into flash. And then you just forgot const expression at the beginning. So what will happen? This data actually will be placed in flash and then will be copied into RAM. And that's what you would like to avoid. And we have additional ELF analysis tool that basically just goes through the whole ELF and analyzes, okay, so who is allocating memory where? It's like, is it memory in the flash region or is this memory in the RAM? And if it's in the RAM, is it new memory? And it just shows us the graph where we can see, okay, in this new pull request, we use it 2 additional pages of flash. And let's say in RAM, we get this block and this block. And that helps, so basically it's a part of the code review where you can find that, for example, okay, I forgot to put const into this variable, and that because of that, I'm actually copying this constant data into memory. Obviously, that's about open source tools, and Flipper is open source tool, where we were trying initially to build toolchain libraries, so everything was initially chosen to be open source, so no proprietary components. But if you are designing something less open source, if you just design normal products, obviously you got much more, much bigger variety of tools. So some specialized vendors like Yar or Seger provide them. Some of those tools are actually quite advanced. So you can, like, all those new chips got ability to trace everything that happens in this chip, like interrupts, how much time you spend in them. But usually these features require quite sophisticated software to control it. And that's where open source tools usually kind of lack support of those additional features. And that's what you can get with proprietary software. And I think that's it from my side.
Yeah, unfortunately, we really don't have much time for any questions, but maybe one question or two.
Terrific overview, thank you.
Yeah, just use the mic.
Yeah, so you said that Cortex-M introduced some features that allowed making operating systems multitask better.
Yeah, they're
what
like dual
did you
stack
mean by that?
capabilities. You can have main stack pointer, and you can have your user thread, user tasks that stack pointer, and you can switch them. You can switch user task thread stack pointer easily when you do the context switch. And in addition, you have pen switch interrupt. That basically the whole like a context switch thing done in pen switch interrupt. And that's what you're doing. So basically you have one routine that performs like a time slice, like tick routine that's called an each tick. And when it sees that, okay, we do need to do the context switch, it basically spawns pending switch interrupt and then delivers. So without those 2 features, like having 2 different stack pointers and having, in addition, pen switch, it's much more difficult to implement traditional operation systems with multitasking. So yes, you can do it on AVR series with some hacks, but it's too difficult to debug it. It's much more difficult to debug it, and it doesn't work in the same way. It doesn't work same predictably and same stable. So probably Cortex-M is not the first MCU that actually introduced it. So obviously there was in the big CPU world, we got those features starting with 286, 386. From early 90s, in the middle of the 80s, early 90s, we got all those features in the big CPUs. But in embedded world, those features arrived quite late.